All right. So Andrew Westphal here. I'm the PI for the Stardust at Home project, and we have on the line with us Dan Zevin and Mike Capraro. I thought what we would do on this Stardust at Home telecon this time is that I would take advantage of the fact that I've just returned from the 2017 Meteoritical Society meeting, which is actually still going on in Santa Fe. I came back a couple of days early. It's usually a week-long meeting, and the Meteoritical Society has been going on now. This is the 80th year that the Meteoritical Society has been meeting. We hosted the meeting 2 years ago in Berkeley. It happens every year, and it's about 400. A meeting of about 400 cosmochemists from all over the world to talk about primitive solar system materials and to talk about primitive solar system history, and that is what we can learn from primitive materials, mostly about the earliest history of the solar system, and then subsequent evolution of planets and asteroids and comets and so on. And so I thought what I would do is to do two things. One is to give a very, very short summary of, I think, quite an exciting development that came up this meeting. It was one of the more exciting meetings I've been to, partly because it feels like we're in the middle of kind of a paradigm shift in understanding of planetary, the earliest history of the solar system. And then I thought I would give my talk, which is about 10 minutes long, or at least it is in the meeting, which is on a fun project which has to do with not only understanding the earliest history of the solar system, but also understanding interstellar dust, which is, of course, something that is fundamentally the interest of the Stardust at Home project. So I'm going to invite Dan and Mike to interrupt me with questions or comments anytime. As I'm talking about these things. This meeting is really for specialists, and so there's a lot of assumed specialized background knowledge. And when you're a specialist, it sometimes is hard to remember, what it's like to not be a specialist and not know, what a particular notation means or something like that. So I'll invite questions as we go along. Okay, so what I'm going to do is share my screen, and let's see, I'll pull up the first slide or a couple of slides. So I hope that you guys can see this. There were there were several talks this meeting that were focused or were taking their inspiration from something called the Warren Gap. And so let me explain what that is. It's a plot coming from a paper by Paul Warren. Paul Warren is a cosmochemist and professor at UCLA. And he wrote a paper in Earth and Planetary Science Letters in 2011, which was showing data that were taken, measurements, I should say, of different kinds of meteorites, and showing the spectacular separation between carbonaceous chondrites and non-carbonaceous chondrites. And so I should take a couple of minutes to explain what these plots are. So these are first I'll start on the left-hand side, and I guess I've cut off the x-axis on that plot, but it is identical to the one on the right, which is epsilon 54 chromium. So what this is so chromium has a number of stable isotopes, but one of them, chromium 54, shows systematic deviations in its abundance from meteorite class to meteorite class or meteorite family. So the epsilon notation there, what that means is it's parts per thousand deviation from the value at the Earth. So if you look on those plots, you'll see that in all cases, the Earth plots at 0, 0 on both of those plots, and that's because these are deviations from the terrestrial value, which is the reference, and that's just for convenience. You could have, in principle, chosen anything. So chromium-54 shows these very tiny deviations from one meteorite group to another, and it turns out so does titanium-50. So titanium also has a number of stable isotopes, and titanium-50 is one that also varies systematically. All of this is possible because of the capability of modern techniques for making these incredibly precise measurements of the abundances of these isotopes in extraterrestrial materials, and so this is really a testament to the improvements, gradual improvements over decades of these instruments. The other, so let me focus now on epsilon 54, the left-hand plot, which is plotting epsilon 54 versus epsilon 50. Epsilon 50 titanium. So the carbonaceous chondrites, as you can see, are all up in the upper right of this plot. And the carbonaceous chondrites have a number of families, which are called CO, CK, CV, CM, CI, CR, and others. These are carbon-rich meteorites that have abundant chondrules in them. Chondrules are these melt droplets that are found in meteorites very commonly. That's where chondrites get their name. So, for example, the CM group, these are meteorites that are chemically and mineralogically similar to the Murchison meteorite. That's where the M comes from in CM. CI is another group, and these are CI are a very special group. They get their name from the first meteorite that was recognized in that family, which is a meteorite called Ivuna. But the most famous one in that grouping is a different meteorite called Orgueil, which fell in southwestern France in the 19th century. And it turns out that CI meteorites, for reasons we don't understand, are both the most altered meteorite, that is, that they've been aqueously processed. They were sitting in water on the asteroid where they came from, asteroid or asteroids. And so the aqueous alteration has destroyed most of the minerals and refractory materials in them. So they're both the most altered meteorite, but also the most pristine in the sense that they match the abundances of the sun much more precisely than any other meteorite. And this is a fundamental question we don't understand at all. It's just an observation. So, so the thing that's remarkable about this plot is that all of these carbonaceous chondrites all plot in the upper part of this plot. On the other hand, the meteorites that are non-carbonaceous, the families like, these are the ordinary chondrites, H, L, LL, EH, which are the instantite chondrites. And then we also have materials from the inner solar system, the Earth, of course, which again plots at 0, 0, or I guess it's actually a little bit off there. I'm not quite sure why that is. The moon is very, very close to the Earth. Mars plots a little bit off. And then these other materials, for example, the Uralites, which are a kind of weird meteorite class that may show signs of explosive volcanism, of all things, on the parent body. All of these are inner solar system materials that, or bodies that all plot in a different region of the plot, so down at the lower left. And then we also have, on the right, we have on the x-axis epsilon 54 again, but now we're plotting against delta oxygen 17. And I need to explain this. This is deviations from the terrestrial fractionation line, or mass-dependent fractionation line of the isotope 17, oxygen. And this is not quite as large, not quite as small deviations. These are now in parts per mil, so that's parts per thousand. That's what that symbol means. That looks kind of like a percent, but it has two little circles at the bottom instead of one. That's a per mil designation, means parts per thousand. And again, we have this same separation between the non-carbonaceous chondrites as well as the terrestrial planets and the carbonaceous chondrites. So there were two things that were new in this conference. One was, I'll talk about, let's see, I need to advance this to the next slide, and I hope you can see it. Did my slide change on the slide? Okay. So the new thing is that there are new measurements made by Kruger et al., and they reported on their results of molybdenum isotopes. Again, this is this epsilon notation, parts per thousand deviation from the Earth. And now it's just two isotopes of molybdenum, molybdenum 94 and molybdenum 95. And these are isotopes that have different nucleosynthetic origins in stars. And what we're finding is that even among iron meteorites, that is, meteorites that are composed entirely of iron metal, that these isotopes also separate out non-carbonaceous and carbonaceous chondrites in the same kind of way as before. And so, whereas before we could not really identify irons, we didn't know where they came from, now with particular iron meteorites, we can tell whether they came from the carbonaceous chondrite reservoir or from the non-carbonaceous chondrite reservoir. And so this is very exciting because it's kind of pulling together a lot of things that before were kind of all over the place. I won't talk about the lower plot except to say it's kind of similar, but has to do with now tungsten isotopes, tungsten 183 and tungsten 182. So, so the way I think I made this analogy to a colleague yesterday in talking about this, feels a little bit like what happened in biology when you could begin to sequence the genomes of different organisms. And you found out that animals that you thought were related to each other because they looked similar for one reason or another, in fact, that they were totally unrelated to each other, and vice versa, that things that didn't look like they were related, like, for example, the hyrax and the elephant turned out to be, closely genetically related. You would never guess by looking at them, but you only know this because of their genomes. And so it feels like we're now being able to get at the genetic relationships between these classes of materials using these new systems. And it really is a very exciting time because it's kind of reshuffling all of these classifications. Things that used to be thought to be in one kind of reservoir are thought to be really in the other now. But the thing I think that really pulls it together, and all of us are all still scratching our heads about this, is a talk that Ed Scott gave. Ed Scott is a cosmochemist at the University of Hawaii. And he proposed that the way to understand these two reservoirs between the non-carbonaceous and the carbonaceous chondrites, and I'll go back to this other slide, the idea is that these really formed in two different reservoirs in the early solar system that were separated either in time or in space. And the thought is probably that they really correspond to separations in space, and that the best way to understand this is that they're separated by Jupiter. So when Jupiter formed, it produced a barrier against migration of material, especially from the outer solar system to the inner solar system. So Ed's proposal is that carbonaceous chondrites formed outside of Jupiter's orbit, and that all the non-carbonaceous chondrites formed inside of Jupiter's orbit. I think this raises a lot of questions that we still don't understand, and maybe I could talk about some of those questions next time, and we might have a little bit more resolution of some of the outstanding questions that are still bopping around in my head about this. But at any rate, it really is a quite a at the same time an exciting time, and also it's just lovely to see these highly precise data, which are experimentally kind of a tour de force in experimental laboratory techniques. So that was a little bit all over the place, I recognize, and I probably went a little fast, but I guess let me stop and ask if there are any questions.
That was interesting. There are a couple things on the slide I didn't understand, like the S-gap or whatever it was on the other slide.
Oh, yeah. Okay.
I didn't know if that was important.
So the R excess and S deficit? Yeah. Okay. So maybe this is something I could talk about in a future conversation. So it turns out that there are two main ways that nature makes elements heavier than about nickel. And fundamentally, the way that these elements are almost all of them are made is by adding neutrons one at a time to seed nuclei around the iron group of elements. So what you do, and I don't have a way to, if I had a whiteboard, I would draw a picture, and maybe I'll prepare this for next time. The way that you make a heavy nuclei all the way up through uranium, and even beyond, is by adding neutrons one at a time to seed nuclei at iron. And but there are two. Nature seems to have done it in one of two different ways. One is in a very slow way, in which the neutrons are added one at a time over thousands, tens of thousands, hundreds of thousands, even millions of years. And we think that happens in heavy stars, in AGB stars, asymptotic giant branch stars, principally, and that the result is that when you add a neutron, that you'll either go to the next stable isotope. So, for example, if you add a neutron to iron 56, you go to iron 57, which is also stable. Then you add another neutron, you go to iron 58. That's also stable. But then you add one more, go to iron 59. That turns out to be unstable, and it beta decays to cobalt 59. And so you've gone one up in Z. So iron is atomic number 26, cobalt is atomic number 27. And if you do this, you work your way up the periodic table, and you populate particular isotopes. So there are some isotopes, in fact, that are only populated by the S process. Some are a mixture of S and R. So S just means slow. It's very simple. R means rapid. So R process elements are what you get when you add neutrons in only a second or two. A whole lot of neutrons all at once. And this is what happens in a supernova. Or the most popular model for the R process is actually merging binary neutron stars. And there you can get elements all the way up to the actinides past uranium, but that's how you get to uranium. You cannot make the uranium by the S process because of a gap. All of this would be more clear if I had some graphics. Anyway, so you can kind of think about these elements, particular isotopes, as either being made by the R process or the S process or some mixture. And we think that what's happening is that those two reservoirs of material inherited different amounts of S process and R process material, and that's the origin of this weird pattern. So the non-carbonaceous and the carbonaceous chondrites. In that upper plot, the carbonaceous are blue. They seem to have inherited more R process material, and molybdenum-95 is an R process isotope. And epsilon-94, molybdenum-94 is I believe, a mixed one. It's got both S and R. And so I'd have to go back and refresh my memory about that, but I believe that's right. So that's the origin of that pattern. But that's a great question. Okay. My talk was about efforts to try to understand the origin of gems. I'll explain that in a minute. And oxidation in the early solar nebula. And what we're doing is something that's new, which is to compare observations of the interstellar medium, that's the ISM, using X-ray, an X-ray observatory in space with our synchrotron X-ray absorption measurements taken in the laboratory. Okay, so let's see. Okay, can you still see my slides? I just went to play mode. So I should explain what GEMS are. GEMS is an acronym. GEMS stands for glass with embedded metals and sulfides. These are enigmatic components of chondritic porous interplanetary dust particles. These are particles that are captured in the stratosphere and are thought to come from comets. And GEMS are common in these particles. But they're really mysterious. And they're about 100 to 500 nanometers in diameter, in that rather restricted size range. They're amorphous silicates with embedded metal and sulfide beads. And there are some pictures in transmission electron microscopes of some of these. And the origin of GEMS has been the subject of hot debate for the last 20 years, with basically two camps. People who, in particular one person, John Bradley, who is advocating that they are in fact interstellar materials, that they come from the interstellar nebula or interstellar medium, and others who advocate the view that GEMS formed in the in the early solar system. So what we're going to do in this talk is to talk about, ask the question, are in fact interstellar silicates GEMS? So the way we do this is using two instruments. So we're using the Advanced Light Source, which is a synchrotron at Lawrence Berkeley Lab. In particular, we're using Beamline 1102, which is a scanning transmission X-ray microprobe. It uses soft X-rays to analyze particles and to measure their spectra in absorption. And so the subject of our study is to analyze GEMS in these chondritic porous IDPs. That is a picture, a SEM picture of a chondritic porous IDP. And the data product of this analysis is an absorption spectrum. In particular, we're focusing on the iron L edge. This is the part of the spectrum where iron atoms absorb X-rays, and they absorb X-rays because of promotion of the 2s electron into the continuum. So a 2s electron gets kicked out of the iron atom, and it produces absorption. And it turns out that the shape of the spectrum is kind of like what you're seeing there, and it's due to the and you get shifts and changes in that spectrum due to the chemical environment of the iron atoms in question that you're analyzing. So in other words, if those iron atoms are in a metal or in a sulfide or in a silicate, then they have different shapes. And so you can tell what the chemical environment of those iron atoms is. The other instrument that we use is the Chandra X-ray Observatory. And what we're doing is to use X-ray continuum emission from X-ray binaries, two particular ones, and we're looking at absorption of X-rays through the interstellar medium. And here the data product is an iron L edge extinction spectrum. And you can see the data are a lot noisier for Chandra because we're counting individual photons, and there aren't that many of them. But as you'll see, the data actually are better than what I'm showing there. And you can see that same step, that's that red line, that's the step in the absorption. Below that, the particular energy, about 700 eV, you get no absorption because of, due to iron, due to the 2s electron absorption, because it's not energetically allowed. But above that energy, you can get it, and that's why you get a step in the absorption. But those two things are different. Absorption and extinction are two different things, because extinction includes both absorption and scattering. And so, so in order to compare one to the other, you would have to either derive extinction from absorption or absorption from extinction in order to be able to compare apples to apples. And it turns out that you can calculate extinction from absorption. So the way we do that is we have a couple of effects we have to take into account. One is overabsorption. If you have a optically thick particle that is thick enough that it can absorb the X-rays strongly, then you get a suppression in the spectral features. And the other thing we have to account for is scattering, and that produces, in those red lines, it produces these pre-edge features, which cause a distortion in the spectrum. So what we do is we take our absorption spectrum that we measure at the synchrotron, we take then the composition and something called the Kramers-Kronig relation to compute the optical constants. These are forward scattering components. And then from those optical components, we integrate over the dust size distribution using something called me-scattering, which is basically computing scattering from spheres, which can have both absorption and scattering. And the result is an absorption spectrum which looks, or extinction spectrum that looks quite different than absorption. Okay, I think in the interest of time, I better skip to our particles. So we looked at 4 different gems. These are TEM images of 4 gems. And here are their absorption spectra in the upper right of this plot. These are the spectrum, and then we're comparing those to some previous work on different gems by Lindsay Keller and Scott Messenger. Then we use those 3 sets of spectra, metal, sulfide, and gems, to fit to data from 2 X-ray binaries, from an X-ray binary called XTE J1817-330 and Cygnus X1, which is the brightest X-ray source in the sky. And so here are our fits. Actually, in the interest of time, I will skip over this one and go straight to the Cygnus measurement. Here you've got a really lovely spectrum, lots and lots of counts, and our fits to the data. And our best fit is that red line. And now I can show that on a ternary diagram. These are contours of confidence intervals, or so-called. So these are the results of our fits to the interstellar medium data. And this is basically what this is showing is that the metal, iron metal that's in the interstellar medium does not reside in these GEMS particles. In fact, it seems to reside in metal phase and in sulfide phase, in a mixture of the two. And in fact, if all the iron and sulfur in the universe were condensed into iron metal and iron sulfide, it would be that tiny little red asterisk that you can see on the left-hand side of those 2 plots. And this is consistent with our measurements. So this is really saying that GEMS are not these interstellar silicates, or to put it the other more properly, interstellar silicates are not actually GEMS. I'll skip over this slide. But more generally, what this is telling us is something maybe even more interesting, which is that in the early solar nebula, that the chemical environment was oxidizing, because it's taking us from metal and sulfide, which are over on the left-hand side of that ternary diagram, and taking it over to the most primitive materials that we have can get our hands on, which are samples from Comet Wild-2 that were collected by the cometary collector of the Stardust mission, and also interplanetary dust particles, which are shown in the green, dashed green and yellow regions of that plot. And so that sort of ghostly, arrow is generally showing oxidation of material chemically. And so this is, as far as we know, the first time that we have any kind of indication of any change. What in fact are the redox conditions of the early solar nebula, and that's because we're able to actually determine the redox conditions of the interstellar medium. And so we don't know yet what this means, but we're just starting with the simple observation. And and I guess I want to say just one more thing, which is that there's a parameter in these fits called A cutoff. I skipped over that slide. And I won't go into details except to say that we think that these X-ray spectra are really also indicating that interstellar dust is, we're beginning to probe the structure of interstellar dust using this X-ray probe instead of the way that it's been done mostly in the past, which is using optical or infrared radiation. Because the X-ray radiation only has a wavelength of 1.7 nanometers, it's much better at being sensitive to structure of dust. And so this is my concluding slide. So, this is really just saying what I said earlier, and maybe I know that this was really aimed at experts. So I'm just wondering if there's anything that I can help fill in terms of unspoken assumptions and so on. So.
Can I ask again to clarify the known gems, what are called gems, known
Yes.
as gems? Where were those collected? How were those collected in the past?
Yeah. So these are the gems, and so gems are observed in these apparently primitive dust particles that are collected in the stratosphere by high-flying aircraft. So NASA, a couple of times a year, sends up these, used to be U-2s, and now they use a different kind of plane. It's an ER, I've forgotten the number. Anyway, it's a spy plane, basically. And they have, it's kind of clever. So what they do is they have these plates, they're very, very clean, that are coated in silicone oil, and they're mounted on the front wing surface of the airplane. And they fly up to a classified altitude. I don't know what altitude it is, some very high altitude. And then they open up doors on these plates, and then they just fly around. It doesn't matter where they fly at all, because these particles are coming down more or less uniformly all over the planet. And they collect a few per hour on the front surfaces of these plates. So I suspect that part of what's going on is that this is giving flight hours to the pilots. So it's doing double duty, but it also is, doing fabulous science. So we have these particles that we think come from comets, but it's really circumstantial evidence. We don't know that for a fact because, the only cometary materials we know for sure come from a comet were collected by the Stardust mission from Comet Wild-2. Because we flew there and flew through the coma. And these are just particles that even to the extent we're confident that they are coming from comets, we have no idea what comets they come from. And
what's the main reason we think they come from comets?
Part of it is just that they contain abundant anhydrous minerals. So these are minerals that have never been exposed to water. And asteroids, every asteroid essentially has had abundant water on it at some point or other. And so you have, so all of the minerals have been exposed to liquid water. And you can see that in the formation of phyllosilicates, clays, that are abundant in hydrous IDPs also. You also find particles that do clearly come from asteroids. But we think that, especially now that we've been to a comet and we have seen no evidence at all in any of the comets that we've been to, or from the samples from Wild-2, we see no evidence for any liquid water, exposure to liquid water. That's a very strong indication that they must be coming from comets. But again, it's there's sort of an uncertainty about this, and it's still an open question. That's why it's so valuable to have samples really know come from a comet.
Right. So Wild-2 samples are not necessarily coming out, not showing gems per se.
That's a great question. And up until now, that's been a puzzle, are there gems in Wild-2 samples? The problem is that when you capture particles in aerogel, you produce things that look like gems. It's really frustrating. And we, in retrospect, it would have been great if the aerogel had been doped with, something weird like thulium or something, so that we can tell, melted aerogel from this amorphous silicate. But just recently, we found a particle in our lab called Andromeda. It seems to be very fine-grained material that was protected by a gigantic sulfide when it was captured in the aerogel, and that protected this fine-grained material. And there we are seeing particles that we're more and more confident really are gems. But they've been heated by capturing aerogel, and so somewhat modified.
Fantastic. Mike, what about you?
No, it's all very interesting stuff. I don't know enough to ask any intelligent questions at this point. I don't believe. I really enjoyed looking at the slides. They're very important. The distinction between the carbonaceous and the non-carbonaceous.
Yeah.
All your explanation there is very clear.
Well, I know that I know that you're a chemist and chemical engineer. Yeah, and that you know, I don't know if it's you know, at all a surprise that we think about conditions in the early solar nebula as being, you know, reduction or oxidation kinds of processes. But that's one of the main things. In fact, one of the things I should have shown, and it actually ties to the original discussion about classification of meteorites. So Urey and Craig in 1950 were the first to put classify meteorites based on something really measurable, and that was the oxidation state of iron. So they made a plot which showed how you could separate iron LL, L, and H meteorites from each other based on the relative amount of iron metal, iron sulfide, and iron 2+. And so that's probably a landmark moment in meteoritics, because up until that point, the classifications had been very sort of descriptive and you know, more like looking at butterflies rather than doing something analytical. So it's really been important.
Well, it's all very fascinating.
So good. Well, I think we've gone up all the way up to Dan's meeting, so we should probably stop here, and I'll stop the video here, and we'll maybe I'll put together, if it's of interest, maybe I'll put together something for next time having to do with nucleosynthesis. That might be a fun topic. So, you know, origin of elements in the universe.
Definitely, yes.
Okay.
Did you find a synchrotron, by the way? You're looking around for one that you might be able to get on for these.
Yeah. So yeah, that's a good question. We so the Canadian Light Source has a Stixum beamline, and they've just opened up their invited requests for proposals. So we're going to be submitting one to there. We're also probably going to be submitting a proposal to the Swiss Light Source. And we also are going to be pushing hard to get we just want a little bit of time on the Stixum at the ALS, but they're going through this big upheaval right now, and so we're not going to cross our fingers. But we did get word, by the way, from JSC last week that they're extracting more tracks for us. They've got 5 tracks that they've identified, and they're working on now. So
okay, yeah, I was going to ask about that.
Yeah. So okay. Good. All right. Well, thank you very much for everything.
Anything from Bulgaria, you might want to share that next time.
That's a good idea. Okay, I will do that. Yeah. Good. All right. Thank you very much. Yep.
I'll mess around with this recording. I'll see if I can get it posted. But maybe next month, Mike, you and I could do a little practice first and try different things before the call.
Yeah.
Sounds good.
Okay, I'm going to stop the video here, and then Mike, I just wanted to mention something. That last night, my younger daughter, Laura, told me that she wants to be a chemical engineer. Yeah, so we're going to...
Well, good for her.
Yeah, and so she's always loved chemistry, and she's a junior in high school, and so we're going to start looking at colleges pretty soon, and so I'd actually be interested in your thoughts about what you think are. This is not something. I'm not a chemical. I don't have a chemical engineering background at all. In fact, I'm barely a chemist. so I'd appreciate any thoughts you have about good programs.
Oh, okay. Yeah, I'll think about that. But depends how far she wants to go away to school, of course.
Well, she's happy to.
So it's been a while since I was in college.
That's okay. Me too.
That's a very broad field nowadays. There's a lot of things she can get into with that background.
Yeah. Well, I think she's most interested in environmental work.
Okay.
I guess a lot of young people are, these days, but she's also interested in space, So one of the things she talked about was developing the chemical tools to be able to develop renewable space flight with renewable fuels, which seems like a very interesting challenge. So
I know when my son went to college, University of Houston actually had one of the better chem engineering programs in the country.
Yeah. Right. Yeah. Did he go to the UH in Clear Lake or?
Oh gee, I don't remember where that, but it was the state college. So the tuition was surprisingly low.
Right.
My son got a full ride scholarship, but when I saw what the amount was that he'd had to pay anyway, it didn't seem like such a big deal.
Right. Right. Yeah. Well, I went to school. I was an undergrad just down the road at Rice, and I know that they had a very good chemical engineering program because of the oil business. But I think Laura would want to. I'm not sure she'd be enthusiastic about that part of it. So.
There'd be more petrochemical there.
Yeah. Exactly. Yeah. Right. Yeah. So.
Okay.
Yeah. Good. Well, thank you for that. Appreciate that. Yeah. All right. So we'll talk again next month. Thank you so much.
Sounds good.
Okay.
See you, Dan.
Bye, everyone. Yeah, good to hear your voice again. Bye.